Thank you. Up until now, we've been looking at motion in one dimension only. And we did make note of the fact that there are both vectors and scalars. That a scalar is a quantity that's just that. It's a quantity. It's a magnitude. It's a value. But a vector is both a magnitude or a quantity and a direction. Now, as long as we were in one dimension only, then all we really had to worry about as far as keeping tabs on direction was a plus or minus sign, going either positive or negative direction. But when we start working in more than one dimension, we're going to start working in two dimensions today, suddenly plus and minus just isn't good enough anymore. Now velocity is a vector that you have to actually keep track of direction. And you will find that there are a lot of things where you need to worry about what is the vector sum of two different quantities, two different vectors. And so this morning we're going to look at how do you add vectors together. How do you describe vectors mathematically? Hey, good morning. So let's, did the sign-in sheet get passed back to him? All right. So the first thing I want you to think about is the word we keep using. We call it scalar as opposed to vector. Ask yourself, why do we call it that? Where did the word scalar come from? What does it mean? Well, we know from past lectures, a scalar is a quantity that's just a value, just a magnitude. It has no direction associated with it. But then why didn't we call it a magnitude or a quantity instead of a scalar? Why did we choose that word for that quantity? And the answer is because you can multiply any vector by a scalar, and in doing so, change its magnitude, change its length. You can make it longer, you can make it shorter. If you multiply a vector, you have a vector that is L long, moving in some direction, and for the moment we don't care about the direction. But if you multiply that vector by a scalar value, a scalar quantity, then you change its direction. Not its direction, you change its magnitude by a quantity by that much quantity, by that much magnitude, by that value. In particular, if you start off with a vector that is 1 unit long, 1 unit. Now, you want to use that as the basis for describing any arbitrary vector of any arbitrary length, as long as it's pointing in the same direction. Now all you have to have is that 1 unit vector and then multiply it by any value of scalar. And you get a vector that's that long now, still pointed in the same direction. Why is that important? Well, because we're working in 2 dimensions now, so let's plot out our 2 Cartesian coordinate axes. You know what? This is going to be more meaningful to you if before I explain this, I explain something to you in more simple, in more general, simpler terms. And that is, how do you add 2 vectors together? And we're going to look at how to do it mathematically, because obviously, as some of you learned yesterday in lab, that is a more accurate way of adding them. But before you do, it helps to understand intuitively, just visually, what you're actually doing when you add 2 vectors. So let's say you have 2 random vectors. You have this vector that is L long at an angle of theta. Okay? Now let's say you have a second vector that is M long at an angle of alpha. What is the vector sum of these 2 vectors? Well, when you add 2 vectors, what you're doing is in your mind, you're taking this vector or the other vector, whichever. You're taking one of them and you're picking it up and you're putting it right at the end point of the first vector. You're maintaining its orientation, its direction, and its length. And now the sum of these 2 vectors, the resultant vector that comes from them, is the vector that starts at their origin and ends at their endpoint. And it is now, well, unfortunate that it came out almost horizontal, but let's pretend that that's horizontal. Okay, that's theta, and this is gamma. So you get a new vector at a new angle with a new magnitude, but that's where it comes from. That's how you get it. You take the first vector, you stick the second vector on the end of it, and then you connect the 2 endpoints. And that vector connecting the 2 endpoints is the vector sum of the 2 vectors. Does everybody understand that so far? Any questions? Anything not quite clear? Okay. Then now, let's go back over here to our Cartesian coordinate axes. And let's define 2 vectors. We're going to define one vector that is exactly 1 unit long along the x-axis. And we're going to call it the unit vector I. And we're going to denote it with a little caret. Everybody know what a caret is? A little chevron. Look, it's a... That is the standard symbol for the unit vector I, which points at an angle. It is defined as 1 unit of magnitude at an angle of 0 degrees or 0 radians. It's parallel to and pointing along the positive x-axis. So, if you want to define any vector that goes to any point on the x-axis, to any arbitrary x-coordinate axis, that vector would be x times the unit vector I, where x is the scalar quantity that scales the unit vector out to the x coordinate. Okay? Now we're going to define a second unit vector. That is 1 unit long and points directly up the y-axis. And we're going to call that unit vector J. J is a unit vector that by definition is 1 unit long at an angle of 90 degrees or 1 unit long at an angle of pi over 2 radians. Now, if you want to, again, by using the y-coordinate as a scalar value, you can define any vector to any coordinate on the y-axis by using that y-coordinate as the scalar, which scales the unit vector J. Now, knowing this and knowing how to add vectors graphically, how would you describe a vector that points from the origin to the point 12, 9 on the Cartesian coordinate plane? This vector, we're going to call it V, can be described in rectangular coordinates or Cartesian coordinates as the vector 12i times plus the vector 9j. Okay? That is this vector. Because how would you add, what is this saying? This is saying 12i, which is, and I'm going to change colors here so we don't confuse it with the unit vector. We're saying we've got a vector 12i and a vector 9j. And the vector sum of those two vectors is this resultant vector v. Because how would you add these two vectors? Well, graphically, you would take this vector, set it here, move it up, and then you would connect the endpoints. I would point out to you that you could also just as easily take this vector, move it here, and connect the endpoints, and you get the same resultant vector. So, that is a vector. And if that's all they're asking for on an exam or on a quiz, once you get to this, you've got an answer for a vector. But What if they ask you for the magnitude of this vector? What would you do if you were told, if you were looking for the magnitude of V? How would you find it? I know some of you know because some of you were here yesterday. Pythagorean's theorem. You have a right angle. So the magnitude of V squared is equal to x squared plus y squared. So if you want the magnitude of the resultant vector, you take the square root of x squared plus y squared, the two Cartesian coordinates. In this case, we've got 12 and 9, so 12 squared plus 9 squared is equal to the square root of 144 plus 81, and that's where I'm going to need someone with a calculator to start doing the arithmetic. Say again? 15. Did it really work out to an exact integer? Wow, I'm good, aren't I? I did not plan that. But y'all don't need to know that. That's just how good I am. So the magnitude of vector V is 15. What about the direction? What direction is it pointing in? What is theta here? How would you find it? How would you find theta? Inverse tangent. That's a really good way to go. Well, we know that theta then can be written as the inverse tangent of y over x, or the inverse tangent of, in this case, 9 over 12. And I'm going to need someone with a calculator to finish that one. $36.8. So we can also write this vector as 15 at an angle of 36.8 degrees. Now, let me give you a pointer, a tip here. If you're working in degrees, be sure to include the little circle to specify this is 36.8 degrees. If you do not put the little circle, then what you're saying is that it's 36.8 radians, which would be a whole nother angle altogether. Okay, so that brings up a topic that you all desperately need to hear. Your calculator will bite you in the backside. I'm sure you've all heard it said that computers are blithering idiots. And they really are. Because if you think about it, all a computer can do is count from 0 to 1. But it can count from 0 to 1 a bajillion times every second. And it doesn't get bored. It doesn't think it's tedious, and it doesn't lose track of signs and decimal places. Your calculator or your computer is an extraordinary tool for doing arithmetic, but you still have to do the math. Your calculator is not a replacement for your brain. Degrees and radians is one example, a perfect example. When you're doing this kind of arithmetic, this kind of math, when you're working with vectors, anytime you're doing trigonometry, you have to make sure that your calculator is either in degree mode or in radian mode, because it will change the answer. On a homework assignment in trig class that I was just grading last night, there was one of the questions that was that told them to use their calculator to find the certain angles at to 2 decimal places. Well, the ones who remembered to put it in radian mode got the right answers, like 0.38, 0.84, 1.57. The ones who did not remember to put it in radian mode, who left it in degree mode, got answers like 0.001, 1 over 100, just way, way off, completely wrong answers. Always make sure you're working in the right mode, degrees or radians. But that's only the beginning of where your calculator will just completely mess you up if you let your brain slide into neutral. When you press when you put in a value and press inverse tangent to find out the angle, how many of you remember what the tangent function looks like when it's graphed out? Bunch of wavy lines. With asymptotes at odd multiples of pi over 2. It's 1 at pi over 4 and minus 1 at minus pi over 4. Think back to your algebra. What's the definition of a function? That for every value of x, you will get one and only one unique value of y. And that's true. You pick any value of x, and it's going to give you one and only one value of y. So this is a function. But if you give it a value of y and ask for the x, there are an infinite number of x's that will give you that value of y. Right? It's up to you and your brain to know which one of those infinite number of x values, which one of those infinite number of angles you're looking for. When you plug in, let me give you an example. Suppose you add 2 vectors, and the resultant vector is right here at 100 degrees. Well, then you've got some minus x and y. And you plug that value in. Well, some very small value of x with a minus x with a large value of minus y, going to give you, something out here. The angle at 100 degrees is going to be just a little past 90. Is that the value you're going to get when you do the inverse tangent? You're going to, what you're going to get is a value over here. Because your calculator is going to give you the value of x that corresponds to that value of y somewhere in this primary domain, this first interval, that minus pi over 2 to pi over 2. If the angle you're looking for is outside of that range, that domain, if it's at more than pi over 2 one way or the other, you're going to get the wrong answer. In particular, if you were looking for something like 100 degrees, you would probably end up getting something like minus 80 degrees. That's why it's important for you to understand visually, graphically, what are you doing when you add these two vectors? What quadrant of this Cartesian coordinate, what direction is it supposed to be pointing? What angle? Approximately. Just you know that it's going to be somewhere a little over 90 degrees. You get minus 80, and you know you're getting the wrong answer for some reason. This is one reason that you can. And in fact, right in that area, depending on your calculator, you'll get a wrong answer using inverse tangent. You can get the same wrong answer using inverse sine, because there are different ways to solve for it. You can solve for it with the tangent, you can solve for it with the sine function, you can solve for it with the cosine function. And because of the algorithm, the way the algorithm sorts all this in your calculator, there's this one area right here where you will get the wrong answer using tangent, you'll get the same wrong answer using sine, you'll only get the right answer using cosine. But if you're just trusting your calculator, it would be, I've seen people do it. They look at it and say, well, I got this answer twice and that answer only once. This must be the right answer. And they were just dead wrong. So, this is why it's important. Most of you are in electrical or electronics programming, right? So, you're going to be working with AC currents, AC voltages, phase shifting signals, whether you're working in power or instrumentation, you're going to be dealing with this stuff. You may think, oh, well, I'm just going to be doing digital circuits and I don't really have to worry about three-phase power and all this. Well, let me tell you what, first time you turn on a microprocessor and it starts doing all sorts of things that it's not supposed to be able to do, you're going to have to learn out about phase shifting signals and how they reflect and transfer back and forth in these conductors very quickly. My point is, all of this is going to matter to you, and it's going to matter a lot in your chosen profession. Don't let your calculator become the crutch that you get, the petard that you get hung on. Use your calculator to do the arithmetic. Use your brain to do the math. It's one of the fundamental rules of problem solving. Once you get an answer, does it make sense? That's always a good question to ask, every time. Now, you've been warned, and forewarned is forearmed. So, bottom line is, we now know two ways to describe the same vector mathematically. This is rectangular or Cartesian form. This is called polar form. Polar form, you give a magnitude and an angle. And the angle is specified in the standard position as starting here at 0, 45 degrees, 90 degrees, 135, well, I hope that's right, 180, 270, 360, or in radians, 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. 0 is horizontal, pointing to the right, and an increasing angles sweep out in the counterclockwise direction. A negative angle, if it's specified as negative, means it's being swept out in the clockwise direction. And just as a refresher from your days in trigonometry, the 4 quadrants are 1, 2, 3, and 4 in order of increasing angle. When you look at a vector in polar form, it should be pretty easy to know what quadrant you're in. Between 0 and 90 degrees, you're in quadrant 1. If you're between 90 and 180, 2. 180 to 270 is 3. 270 to 360 is 4. It's just as easy to tell when you're looking at a vector in rectangular coordinates. Can anyone tell me how? If both coefficients are positive, then you're in vector 1. If the x coordinate or the I vector is negative and the y vector or the j vector is positive, you're in quadrant 2. If they're both negative, you're in quadrant 3. And if the x is positive and the y is negative, you're in quadrant 4. Just look at the coordinates of the two vectors, or at the direction. And that'll tell you what vector you're in, what quadrant you're in, which will help you when you're trying to decide whether that tangent button gave you the right answer or not. What if you wanted to add, let's say we've got one vector of 20 at an angle of 30 degrees, and another vector of, you know what? I am going to be smart. We're going to make this come out to a nice even integer. Yeah, you know what? No, I'm not going to do that. Let's go 30 at 45 degrees. How would you add those two vectors together? Exactly. We got to convert them into rectangular or Cartesian form. You can add vectors when they're in this form, or subtract them, because subtraction is just addition of a negative. If you want to multiply or divide, because division is just multiplication by a reciprocal, then you need them in polar form. And we'll get to that later. But right now, how would we convert these two vectors into rectangular form? Sine and cosine, that's right. Somebody help me out. Let's call this V1 and this V2. In rectangular coordinates, V1 becomes, what's the x coordinate? What's the x component? Cosine of 30 degrees, I plus 20 times the sine of 30 degrees, J. And somebody with a calculator do the arithmetic. $17.32I. $10 even? How did that happen? Oh, because sine of 30 degrees is 1/2. That's right. Okay, that's the first one. What's V2? Everybody say it out loud with me. So is it out loud that y'all don't understand? Which one of those words confused you? Come on, everybody, let's recite it. 30 cosine 45 degrees I plus 30 sine 45 degrees J. And yeah, you feel silly saying it out loud, but repetition will burn it into your brain. And it will become second nature for you to look at this stuff and just see it like this automatically if you do it, if you just go through the repetition. Somebody do the arithmetic? A whole class full of engineering students and not a calculator in the bunch, right? Why don't I buy that? 21.21 I. Okay, and the same on J? Why would that be? Because sine and cosine of 45 degrees, 1 over the square root of 2. Both. It's exactly in the middle, so that both sine and cosine are the same. Now, adding them together is just a matter of $17.32 plus 21.21 I plus 10 plus 21.21 J. Well, I can do this one. It's 31.21 J plus 38.53 I. Did I do that right? All right. So, we'll call this V3. Then V3 is equal to this in rectangular form. Now somebody give it to me in polar form. Who's got it in polar form? $49.5. At what angle? Nope. Say again? 39 degrees. Yeah. Let's see, did we cover everything in these? Yeah, we did. We surely did. Very good. Now I want to show you one more thing. And this has to do with what I was telling you before. You need to do the math with your brain, do the arithmetic with your computer. So, let's say we have a vector 1 that has 25 meters per second at an angle theta. And we have another vector, v2, that is 20 meters per second at an angle of beta. What if we take the vector sum of these two vectors? Could you look at the resultant sum? You go through the conversion, you put them into Cartesian rectangular coordinates, or the rectangular form, you add them together, you convert them back into polar form. Could you look at that resultant vector sum in polar form and know if it was reasonable or not? Now, we don't know what these angles are. We know as one is theta and the other is beta, so they're not the same angle. What would be the maximum possible value for the vector sum of these two vectors? The magnitude of the vector sum is maximum when theta is equal to beta. Because when theta is equal to beta, doesn't matter what it is, V1 plus V2 is simply the arithmetic sum of the two. In this case, 25 plus 20, or 45 meters per second. When they're both pointing in the same direction, they just add together to make one big long vector, and you get the full magnitude of both. What would be the lowest possible magnitude of a resultant vector sum? The magnitude of V sum minimum will happen when theta equals beta minus 180 degrees, or beta minus pi, when they're pointing in exactly opposite directions, because now look at the vector sum. Here's V1, and V2 is pointing in the opposite direction. There's your vector sum. So in this case, it would be 25 minus 20, or 5 meters per second. So when you look at these two vectors in polar form, you can just look at them and know immediately that your resultant sum, your resultant vector is going to be somewhere between 5 meters per second and 45 meters per second. So if you go through all the machinations and you come out with 50 meters per second, you know right off the bat, you know you did something wrong somewhere. Any questions? Comments? Thoughts? All right. Well, then have a good weekend, and I will see you all on Monday. Everybody sign the sheet? Anybody not sign in?
Did we have one for yesterday?
Yeah, you turned in a lab report.
No. I mean the signing sheet.
No, it was. No, you didn't. Whoever turned in a lab report was present.
Okay.
There you go. But yeah, if you were here, you did the lab, you were marked present. You bet. Oh. Hey, good morning.
Morning. How are you?
I am not dead yet. Say again? We are. Are y'all it? We give everybody another half a minute. Then there's somebody showed up. Here, start signing in. Brand new month. February. Oh man, I never stopped recording.